All right, let's begin. We're good. Chapter 7. It deals with something called linear systems. So let's talk about that first before we get into details here. Other textbooks, what they usually do, they do it right after the graphing section. So according to, when was the graphing section? What was the graphing chapter in our book? When did we start graphing? I think it was 3, right? Because 2 was solving equations, 3 was graphing. So most textbooks, they have this right after the graphing section. I think that's probably the more appropriate place for it here. Because we're going to do some graphing. They're going to deal with a few other things here as well. So, what in the world is a system anyways? System just means you have more than one equation. So notice some examples here. You have x plus y equals 3. That's an equation. And then you also have 3x plus 4y equals 2. So you got 2 equations. In Math 63, we go on a little bit further, then we get 3 equations. And then you get into higher mathematics, and you have like 96 different equations. 200 different equations, depending on what it is. Just maybe a quick example, where is this coming from? When I was an undergrad student at Fresno State, the professor there was good friends with the accountant for Nike shoes. It's like, dude, that's kind of cool. So they were saying, he said that his friend told him they have 96 different equations they work with to figure out the price set for a shoe. So anything that you can think of, endorsement costs, does that have an equation with it? Absolutely. Raw material costs, another equation. So every facet of the production process, they write up an equation for it here. So workers' compensation for the workers, there it is. Distribution costs. I mean, all these things really go into this whole concept of different equations. And what they do is they look at, these are equations here. When Nike shoes looks at it, they're more like inequalities. There's a little zone, they say, okay, this is the best zone for the price of the shoe. They even have an equation for per region or per city, I think it's per city, is expendable income. Ever heard that term before? It's the difference between the cost of living in the area and what people make in the area. And that always fluctuates, right? Almost like monthly, depending on what people got and all that stuff. So they even have an equation for that. And they say, okay, based upon this, based upon the expendable income in this area, we're going to price this shoe at this dollar amount. But again, close to 100 different equations that they deal with, which I thought was kind of cool. We're going to deal with 2, okay? I think 2 is enough. Okay. So first of all, we're going to learn different ways to solve these systems. So 7.1 uses the graphing method. 7.2, we're going to talk about something called the elimination method, or the addition method, some books call it. 7.3 is something called the substitution method. So we're going to have these sort of like different methods to solve these equations. And then 7.4 is the application section. Let's start applying stuff. Okay. 7.1 is a pretty good way to review graphing for us, which is be a good thing since it's the end of the term. Be a good way to review graphing. Another thing is graphing is not the best way to solve this, and we'll take a look at maybe one problem that we're going to have when we solve this. But the graphs need to be pretty much precise. Could you imagine trying to get on a graph sheet of paper the answer of like 1/12? I don't think we can get 1/12 on a graph sheet of paper. That's just not precise enough. Or how about anybody want to graph out to like 3 million on a graph sheet of paper? Nah, so graphing really is not, first of all, is not precise enough for fractions, and then it's not big enough to really handle a big, humongous numbers. So I've got 2 issues there. So we're going to take a look at it and just give us our definitions. What are we really trying to do in this something called systems? And with that, then we'll learn 7.2, 7.3 are really going to be the methods we're going to use. So we're sort of going to taper off of the graphing method, learn some other stuff. All right, with that said, let's take a look at it. So instead of graphing one line, what we really have in our cells, we have 2 different lines. And let me go back real quick here. Since you have 2 equations, isn't x plus y going to create a line? X plus y equals 3. 3x plus 4y equals 2 is going to create another line. So now in this case we have two different lines, but they're graphed on the same x and y grid. So what can happen? You got the red line, got the blue line. It could happen that they actually intersect at a certain spot along the graph. We good there? If that is the case, we have ourselves one solution, and that's exactly what we're trying to find. This whole entire chapter, we're just going to try to figure out where's this intersection point between between the two graphs. And this intersection point, that is going to be the answer. We good? All right, jumping to this one here.
Carry on.
All right. Also, it could be this, that the blue line and the red line are exactly parallel. Will they ever cross? No way. They will never cross. Therefore, we actually have no solution. There's never a time where we're going to find the intersection point between these two things. And that's okay. Just means we don't have a solution. There's a little name for it. We call it the system is inconsistent. Again, I'll just sort of use these vocabularies throughout. So no solution. Graphically means the lines are parallel. Algebraically, we mean the system is inconsistent. We're good? Next one. It could be that the blue line and the red line actually right on top of each other. Can't see the blue line because it was graphed first. Now I've got a red line on top of that one, but there's a blue line underneath it. And so in this case, there's a whole bunch of answers. In fact, every single point that's on the red line is technically also on the blue line. Is that right? Okay, so graphically what we say is we say the lines coincide, which means they're just right on top of each other. Okay, algebraically we say the equations are dependent, or the system is dependent, whichever way you want to say it. Okay, we good there? That's the intro. Let's jump to some problems here. Okay, first things first. On your matched problems here, I don't like the little 2 next to the x. So can you guys just scratch off that 2? It should be just x plus y equals 4. Again, when the person was doing it, he got a little sleepy here. No, it's so weird. The example problems in the textbook here, they don't include fractions as much. But then the match problems, they include these weird fractions. I'm like, no, that's not what we want to see right now. I want to sort of just get the feel of this, how to graph these. Anyways, let's go for it. So x plus y equals 4, and then x minus y equals 0. We're going to graph these. And if you think back all the way to chapter 3, if you have x and y both on the same side, we do this by intercept method. Remember the intercept method a long time ago? It means this right here. We put x plus y equals 0. Oh, so x plus y equals 4. We make a quick little table. Is that right? What's the easiest number to plug in? 0. Plug a 0 in for x. What would y have to be? 4 is good. Okay. Right. Plug in a 0 in for the x value. That means y has to equal 4 because the x disappears. Good there? All right. Let's go the other way. Remember, let's plug in a 0 in for the y. What would x have to be if that to be true? Think about the equation here. 0 comes in for this little y here.
4.
That disappears, and x equals 4. Okay, that's one set. We got this equation. Remember, we just need 2 points to determine a line, right? Jump over here. This is where this is the only time where the intercept method does not work, and they gave it to you right off the bat. The reason why it does not work is when you plug in a 0 in for the x, what is y going to be? Yeah, after a little bit of work, negative y is equal to 0. Divide through by negative 1, but we get ourselves 0. Okay, the intercept method does not work here because you only have one single point. So plug in any other point in the whole entire world except for 0. 1 is good. Yep, I plugged in a 2, and that's still okay, whichever. I plugged in a 2 for the x. If you want to plug in a 1 for the x, go for it. But your job is to figure out what in the world is the y value. So all yours. Alright, and again, plug it in. I get 2 minus y equals 0. You might have 1 minus y equals 0. That's fine too. Subtract the 2 from both sides. You get negative y is equal to negative 2. Divide through by negative, and I get myself a 2, 2. If you got a 1, you probably got a 1, 1 then. Anyways, think we're ready to graph here, so go for it. Can you graph both of these? The red one and the blue one. And I'll give you a little bit of time to try it yourself. Alright, and look at this here. Let's see. So 0, 4 is right there. 4, 0 is right there, connected with a straight line. Hopefully more straighter than mine. Okay, the blue line, how about 0, 0? How about a 2, 2? In fact, actually, that 2, 2 right there, isn't that actually the intersection point itself? So when we do that, then we get ourselves 2, 2 done. That is the point, and the whole point of this whole entire chapter is to figure out that intersection point right there. Okay, and then we can sort of test it algebraically as well. So real quick, if this makes sense, if we plug it back to the original, 2 plus 2 equals 4, is that right? And then 2 minus 2 equals 0, is that right? Yep, perfect. Okay, so it really is the solution to both of these at the same time. So now we call 2, 2 is actually a solution to the system.
So all you do is solution. You get the ring.
Yep, if your intercept is correct, intercept point is correct, you should be able to plug in that into both equations and both of them should be true. Yeah. The previous textbooks that we had actually made you do that. It said this is a potential answer because it got a graph answer, and then you had to actually plug it in to verify. But as long as you have a graph correctly, as long as you're doing it correctly, that's fine. Okay. Next one, I'll let you guys try this one yourself. Alright, I'm going to start as well just to make sure we're good to go. So same exact concept here, x plus y equals 3, plug in a 0 for the x, get a 3 for the y. A 0 for the y makes a 3 for the x. On the other side, plug in a 0 gets you a -1 this time. 0 for the y gets you a +1 for the x. Hopefully we got that. I think everybody has got that. Alright, and graphing. So 0, 3, 3, 0, there's my graph. Then 0, -1 is going to be down there. And then 1, 0 is going to be about right there. And then this time as we graph it, none of the points that we chose actually is the intersection point, but can we extrapolate what the intersection point should be?
Isn't it supposed to go that way? The line? Aren't they supposed to be parallel?
They should not be parallel.
No?
No, maybe if anything your sign is off or something like that. I think maybe if anything the sign is off on here. 0 should be 0, -1 for the y value because of the minus sign right there.
I was wondering how you wrote one with no signs because you scratched that out. I didn't realize that.
Got it. Yeah, don't forget on number 2, the 1/2 is scratched out. It should be x minus y equals 1. Alright, so the point that we have, any of the points that we used, they're not intersect points, but extrapolating, what is that point right there? I think it's 2, 1. It may be a little bit difficult to see here. If you have a little straight edge, maybe that's the best way to graph it, so you have a better idea there. But again, algebraically, think about it here. 2, 1. 2 plus 1 equals 3? Yep. 2 minus 1 is equal to 1? Yeah, they work out algebraically. Okay, then again, that was a good review of graphing by intercepts. We good? Let's jump to the different type of graphing, which is graphing by using y equals mx plus b. That's the other type we learned in chapter 3. So it's this one here. And I have my little green star over here, which means I'm going to do this incorrectly. We'll see what happens. Just the graph is not all that straight. That's all. That's kind of what happens. But we can graph it. You just need to make a better graph than me. Okay? So let's go for it here, and then I'll redo it here. So y is equal to 2x minus 9. Y is equal to 3. Notice both of them are solved for y. If both of them are solved for y, we can use this little method right here. Remember that one? All the way from chapter 3. That guy is my slope. The b value all the way at the end is something called the y-intercept. And remember, for this problem, you don't even need to write anything down. You should be able just to look at the numbers, graph it, done. Okay, the only little issue here with this graph is notice the lines here, 1, 2, 3, 4, 5. We have 5 lines and we're already at 10, so that means each of these lines represents 2 instead of 1. So careful when you graph it. But let's go for it here. So 2x minus 9, what should we do first? We're going to go along the y-axis down to -9. So if these guys are both represent 2, this is 2, 4, 6, 8, and then 9 would be about right there. Alright, slope of 2, technically 2 over 1, right? So we're going to rise 2, and we're going to run to the right once. So kind of carefully here, you go 1, 2, up, 1 over, and you're actually dead center of the square over here this time. Good there, you're not on any one of the lines. Alright, and then again, if you want to, you can go on. You can go up 2, 1 over. Eventually, you make a little line like that. Again, use a straight edge. Use something that's going to give you a pretty good graph. Alright, and then the other weird one here, y equals 3. Do you guys remember how to graph that one? What is that anyways?
Isn't it just
Ah, yeah. Horizontal or vertical? Which one?
horizontal?
Horizontal. Which way is horizontal? Goes straight across, right? If it was x equals 3, then it goes up and down. That's vertical. Since it's y equals 3, that means it goes straight across. So find y equals 3 here. This is going to be 2. That's 4, so that means it's 3 is right here. And it's a line that's going straight across. Okay, what's my intersection point? I need 2 numbers, right? I need the x coordinate, y coordinate. So 3 and 5, or 5 and 3, which one? I think it's probably 5 and 3, right? 1, 2, that's 5 in the middle, 3 up, about right there. Okay, again, I'm not quite sure. So if I say 5, 3, I maybe put a little question mark here. Let's see. Second equation, does it work out for the second equation? Of course it does, right? Because y is actually equal to 3. But I'm not sure whether it works out for the first equation. So can you plug in 5, 3 into the first equation? Let's just see if it does work out.
So is it 6 and 3?
Oh, okay, so once it's 6 and 3. Okay, let me just check this out then. So as the y becomes 3, I'm going to plug it in here. So 3 equals 2 times the x value, which I know to be 5, minus 9. In this case, that's 10, and 10 minus 9 is not. Oh no. Bummer. Christina got it wrong. Christina got it wrong. Okay, so that's what I said. You do need a good straight edge, because if you kind of notice, what I did is I curved the line just so right over here. Just slightly. So let me redo the problem just really quick. And I'm going to put in more dots this time. So this is my -9, up 2 over 1, 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 up 2 over 1. Hey, look at that. It crosses right here. So it doesn't cross at 5, it actually crosses at 6. So 6, 3. Now, can anybody verify that, just to make sure, or if you have already? So this is kind of interesting. Another thing I want to point out. Look at this. We're solving a algebra problem, right? Because you don't see a graph here anywhere here. We're using geometry to solve it, and then we're using algebra to check it. So this sort of things are so intermixed. Okay, the 6, 3 check out? Okay, perfect. Okay, checks out for the bottom, because y is equal the bottom equation, because that y is equal to 3. For the top, it's 2 times 6 is 12, and 12 subtract 9 is actually a 3. Perfect. Okay, so 6, 3 is truly the final answer. Okay, so just to sort of reiterate again, all we're just trying to do is figure out the intersection point. That's it. It'd be a good way to practice graphing, especially towards the end of the semester. But we're just trying to figure out that little point right there. Okay, now let's take a look at the two weird ones. So x is equal to y plus 5, x is equal to y minus 3. Alright, the first thing is I don't like the fact it's solved for x. I would appreciate it if it was solved for y, because then I can use y equals mx plus b. So what should we do to the top equation to make it solved for y?
Subtract y. Subtract x.
If I subtract x, it's going to give me x over here, and then I got 0 is equal to y minus x plus 5. Everything's on one side, and I don't like that. How about this? How if I subtract 5? If I bring this 5 over to this side, would that work? So bringing the 5 over to this side makes y is equal to x minus 5. Everybody good there? Alright, and graphing it. So negative a, good. And also the graph paper goes up by 1s and down by 1s, so that's good. So starting off down, bottom, negative 5. What's my slope?
Up 1 over 1.
Yep, it's a 1, technically 1 over 1. So up 1, 1 to the right. And again, you could do this forever if you like. Up 1 over 1, just to give you a nice straight graph. Just so we won't mess up like I messed up on number 3. Alright, you guys get the next one. You can graph the x is equal to y minus 3. Again, don't like the fact it's solved for x. Would really appreciate it if it's solved for y. So the blue line here, add 3 to both sides. Like that would make y is equal to x plus 3. Everybody okay with the equation itself? Alright, then going up here, starting at 3. So 1, 2, 3, looks like about here. What's my slope? 1 over 1, huh? So 1 up, 1 over, 1 up, 1 over, as long as you like. And then connect them. So what makes lines parallel to each other? I don't know. Isn't slope what makes lines parallel to each other? See, because if I had a different slope, if this was a slope of 2, the red line would be going up much faster than the blue line, right? Eventually they would cross. So the giveaway is the fact that right over here, you have the same exact slope on both of them. And you have a different y-intercept. And because of that, that means these guys will never cross because they're going up the same amount. Or if there's a negative slope, then they'd be going down the same amount each time, so they will never cross. So kind of careful, the slope sort of gives it away right there. Okay, answer to this one. 0 with a little slash through it, which means no solution, or you can just write it out. No solution. Alright, good there. And the other one, which we've sort of seen already before. Jumping to this here, I'm going to change the numbers on you so it doesn't turn out to be weird fractions here. So change that 5 into a 6, change the 15 into an 18. That'd be a little bit easier for us to sort of graph and handle. Cool. All right, so let's go for it here. We could do intercepts, and again, your choice. You could do intercepts, go for it, or you could solve this for y. Normally in algebra, we like to solve for y, because then we see exactly what the slope is going to be, we see exactly what the y-intercept will be, and then we start graphing. So in this case, I'm going to solve for y. What should I do first? Subtract 4x. Perfect. 3y is the only thing that's left on the left. So subtract 4x makes a negative 4x plus 6. And next, what should we do?
Divide by 3.
Divide by 3 is perfect. So we get y equals
Negative 4 over 3.
negative 4 over 3. X plus 6 divided by 3 is a 2. Perfect. Okay, all yours for the second equation. Solve that one for y as well.
What if it's the same?
That's why. Let's go for it. So we've seen it already here. So subtract 12x from both sides gives you a 9y on one side, negative 12x plus 18 on the other. Dividing everything by 9 and gives us y is equal to negative, let's see, divide by 3, so negative 4 over 3x. Everybody good there? Plus 2, and so notice, yes, the red equation, the blue equation, they actually are the same exact equation. In that case, you know the lines are going to be on top of each other. Yep, so the red line starts off at 2, goes down 4, 3 to the right. There's my red line. My blue line is going to start at the exact same spot, go down the exact same amount, over to the right the exact same amount, and so we've got this situation happening. The lines, really both lines are right on top of each other. So we're going to do two different ways. We'll start off 7.1. 7.1 just wants to make you realize that it's really any point on the line is going to be a solution for both. We good? And then we're going to be sophisticated. Later on, we're just going to say lines coincide. We're going to give the geometry answer to these. Then Math 63, you get a little bit more sophisticated. You actually say what the solution is, but that'll be for sometime later. Okay, so really trying to find intersection point. Number 4 showed us that you can have no solution because they're parallel. Number 5 showed us that you can have infinitely many solutions. So any point on the line is a solution for both. And what the geometric term for it is that lines coincide. Okay, that is the end of 7.1.